one more video on the law of sines. So in the previous video, we saw how we could use the law of sines in the case where we were given two angles and a side. Because when you're given two angles, you're really given all three angles. And if you have all three angles and a side, you can use the law of sines to figure out the remaining two sides and do what's called solve the triangle. Find all the angles and all the sides. It turns out the law of sines is applicable in a different case. The case when you have two sides and an angle. And it turns out that the angle can't be the angle included in those two sides. So it's what's referred to as the side-side angle case. More on that once we get to 8.2. And it'll turn out that this case, when you have two sides instead of two angles, is a little bit harder. It's sometimes referred to as the ambiguous case. And I can demonstrate why it has that name with this example. So we have this triangle ABC, and we know that angle A is 45 degrees and side length A is 2. Note that the picture's not drawn for us, and that's intentional. We can try to draw a picture, but you got to be a little bit careful when you're drawing these triangles because you might not be drawing them to scale. More on that later. So anyways, if we put 45 degrees down here somewhat arbitrarily, then 2 has to be over here because little a has to be opposite capital A. And then B can be wherever I want. I don't know, maybe I'll toss it over here. But if I put little b over here, then this must be capital B. And then by process of elimination, capital C goes up here and little c goes down here. And so maybe we're asked to find the two unknown angles and the one unknown side length. And you're like, all right, what order should I go in? Does it even matter? It does matter. We can't figure out capital C or little c right now because if you go back to your law of sines, we have to choose two of these three fractions and equate them together. And if we choose the sine of capital C divided by little c, then we'll have two unknowns, capital C and little c, and that'll be problematic. What we need to do is choose two of these fractions so that there's only one unknown. Well, since we know capital A and little a, and we know little b, we can find capital B by choosing these first two and getting this equation right here. So let's go plug it in some numbers. Capital A is 45 degrees, little a is 2, and little b is root 6. So that gives me this equation here. I want to find capital B. To get this by itself, maybe I'll multiply the root 6 over to the top over here. And now that I've got sine of B all by itself, I can evaluate the sine of 45 degrees. Let's see, that's the square root of 2 over 2. So I get the square root of 6 times the square root of 2 over 2 divided by 2. Let's see if that simplifies it all. I can think about the top as the square root of 12 divided by 2. And I think about the bottom as 2 divided by 1. And then I can flip those fractions upside down. And I get the square root of 12 divided by 4. So the sine of B equals the square root of 12 over 4, and somehow I'm supposed to use that to figure out capital B? Well, I chose these numbers really carefully to make sure that this was one of the values off your unit circle. It won't always be, but in this case it is. And you're like, nah, you're crazy. I don't remember that off my unit circle at all. Right, but the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 is just the number 2. So this is just 2 root 3 over 4. And this 2 and this 4 can cancel, and I get root 3 over 2. What I'm saying is sine of B is root 3 over 2. And you're like, oh, okay, I got this. B is, 60 degrees? Well, careful here. On your unit circle, the sign refers to the y-coordinate. The y-coordinate equals root 3 over 2 somewhere up here, but there's two different points on your unit circle where that happens, over here and over here. Yeah, 60 degrees is one of them, but the sine of 120 degrees is also equal to root 3 over 2. What I'm saying is there's two possible answers for B. Wait, there's two possible answers? That's really weird. You're telling me this is an ambiguous question? Yup. It's called the ambiguous case. The idea is when you're given two sides and an angle, there might be two different solutions. Wait, how is that possible? How could you draw this triangle where this side length is root 6 and this side length is 2 and this is 45 and get two different solutions for capital B? Well, let me show you the picture. Capital B equaling 60 degrees would be something like what is pictured here. Capital B being equal to 120 degrees. 120 degrees would form a triangle something like what you see in green. Note that the big triangle in red and the little triangle in green both have an angle of 45 degrees here, and they both share this side length of root 6. And if the length from here to here is 2, maybe you'd believe that the length from here to somewhere down here could also be equal to 2. Whoa, so anytime I have side-side angle, there's always going to be two possible triangles? No, it turns out. There could be 2, there could be 1, or there could be 0. More on that later. In this case, there ended up being 2. Capital B could be 60 degrees or 120 degrees. How do I know that? Well, because the sine of B equals root 3 over 2, and for both 60 degrees and 120 degrees, the sine of that angle equals root 3 over 2, and this part's important, These are both possible angles. You're like, what do you mean possible angles? Remember, the sum of the interior angles in a triangle has to be 180 degrees. I used up 45 degrees here, so that means that I have 135 left over for my remaining two angles. Both 60 and 120 are less than that 135, so I'm good. But maybe you can imagine another case where this was, I don't know, 70 degrees. And I used up 70 degrees and then I got these two answers. You'd have to look at these and be like, well, this is possible because 70 plus 60 is 130 and that doesn't exceed my maximum of 180 degrees. But 70 plus 120 degrees would be 190 degrees and that would exceed the maximum that I have for the sum of my interior angles. The sum of the three interior angles has to be 180 degrees. You can't use up more degrees than you have. So if this were 70 degrees instead of 45 degrees and you solved for these two values of b, you'd have to recognize that this is not a real solution and there's only one value of b here. In this case, there's two values of b, but it's also possible there's one. And in the last example, I'll show you how it's possible that there's none. Okay, but from a more practical point of view, how do I know which of these to use? Like, how do you want me, the student, to tell you, the teacher, my answer? Well, there's a few options there. One option is the problem could say something like, assume this is an obtuse triangle, or assume angle B is obtuse. Obtuse means this is more than 90 degrees. So when you get to this stage, you're like, it must be talking about this one here, not this one here. Another thing that you can do is add a note that says there's two different triangles that could satisfy this. So tell me what capital B, capital C, and little c are in each of the two cases. For what it's worth, that's pretty hard, and I typically save that for just the case of extra credit on exams and stuff, but it can be done, and I want to demonstrate how in this example. If B equals 60 degrees, I have that A is 45 degrees. Now I know that B is 60 degrees. I know that the sum of my three angles has to be 180 degrees. So if I'm using up 105 here, I have 75 left over for C. Little a and little b were given to me in the problem. Those are equal to 2 and root 6 respectively. So all that's left to figure out is what little c is equal to. Well, to figure out little c, I can use my law of sines. I'll have to include this thing here so that I can solve for little c, and I can grab either of these two guys here because I know capital A, capital B, and little b. It doesn't matter which one you choose. I'm going to arbitrarily choose this one. The sine of A over A equals the sine of C over C. A is 45 degrees. Little a is 2. Capital C is 75 degrees. Little c, I don't know. I want to solve for it. Maybe I'll first solve for it and then plug in values. So multiply the c up to the top here, the 2 up to the top here, and the sine 45 down here. That gives me this expression for c, which we saw in the previous video is kind of annoying. Sine of 45 degrees is easy. You have that on your unit circle. But the sine of 75 degrees, that's a pain to do. You could use the angle addition formula like we did up here and figure out that that's equal to root 2 plus root 6 over 4. So you get this mess of an expression for c. You cancel out this 2 and part of this 4 and then flip this upside down. And I think what will happen is you'll get that c is root 2 plus root 6 divided by 2 now after these cancel times 2 over root 2. These 2's cancel and you're left with root 2 plus root 6 over root 2, which I guess you could rationalize the denominator, multiply the top and the bottom by the square root of 2. The square root of 2 times this 2 will give me 2. The square root of 2 times this square root of 6 gives me the square root of 12, which I can rewrite as 2 times the square root of 3. And in the denominator, the square root of 2 times the square root of 2 is just 2. And now I can cancel out this 2, and this 2, and get 1 plus square root of 3 as my answer. That's some pretty challenging algebra getting there. Plus, it's a little bit annoying using this angle addition formula up here. Really, the key, what I'm trying to get you to understand is, could you set up this equation right here? And if you can set up this equation right here, you understand all of the new stuff for this section. So c equals 1 plus the square root of 3. Well, that's one of the solutions for c. That's the solution that corresponds with choosing 60 degrees for this angle of capital B. But remember, capital B could have been 60 degrees or 120 degrees. If capital B is 120 degrees, well, then I'm using up 165 degrees between A and B. So that leaves me with just 15 degrees left over for capital C. I still know that little a is equal to 2 and little b is equal to root 6, and I could solve for what little c would be equal to. The way I do it is I set up using my law of sines. I'm going to again choose sine of a over a equals sine of c over c, although I could have decided to use sine of b over b equals sine of c over c. As long as I include this sine of c over c, I'm good, and I can figure out this one. To get this little c by itself, multiply it to the top over here, multiply the little a here, divide the sine of a over here, and you get c equals a sine of capital C divided by the sine of capital A. Now I can plug in, a is equal to 2, sine of c is the sine of 15 degrees, not looking forward to that. Sine of capital A is the sine of 45 degrees. Sine of 15 degrees, you could get there using the half angle formula, or you could get there using the angle addition or subtraction formulas. I think we've done that one already too. But maybe I can do it again really quick off to the side. I don't know, maybe I'll use angle subtraction because I have those memorized better. 15 degrees is the same as 45 degrees minus 30 degrees. And the angle subtraction formula, I'm going to have a hard time writing this, tells me that this is the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. And these are all values off the unit circle. Sine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. And then I want to subtract. Cosine of 45 is root 2 over 2. Sine of 30 is 1/2. So I get root 6 minus root 2 over 4 as the value for the sine of 15 degrees. I can go plugging that in down here for this sine of 15 degrees, and then sine of 45 degrees is root 2 over 2, and I guess I could simplify this mess, and that would be my final answer. Let's see, what I have written here is almost the same as what I have written right here. The only difference is I have a plus sign here and a minus sign here. So I think if I went through all these same steps, all that would happen is the square root of 2 would be negative. So the square root of 2 changes in over here, changes here, here, ends up being this 1. What I'm saying is I think if you go through all the simplification steps, you'll get negative 1 plus the square root of 3. Or the square root of 3 minus 1 might be a better way to write that. At any rate, that's my value for C, which would be this tiny little side length here, this value C for this little triangle, if I chose to make this angle, capital B, 120 degrees instead of 60 degrees. That's a lot. I was going to make this the last video. I feel like I need one more short video on this ambiguous case, and then I'll call this good.